We have a number of questions that have been sent in that I'm going to address first on the homework. And the first one is 63 and 65, a pair of them. So as we look at that on section 5.5, 63 and 65. So we're on page 324, and in 324, number 63, now I can see why the question was asked in both of those. Okay, let's cut to that, Debbie. The 63rd problem is a case where it looks like we're going to have to regroup everything, and what you have is a common p plus 1. And then we're going to have a trinomial left over, which we then hopefully can factor. At least that's our goal. So as we look at the problem, I'm going to bring everything over to the left side. Let's leave that there for a moment while I write it on the board. So I have number 63, and I'm going to take 6p squared times p plus 1. Then I'm going to have that equal to 4p times p plus 1. And then I'm going to have minus 5p times p plus 1, and I left out a letter. Is that? That is the problem, because I was noticing I didn't want that in every term, and now I've managed to mess that up. Okay, what are we going to do there to try to salvage that? Make it look neat. There. Okay, coming off the document cam, I'm going to do this in one step here and have 6p squared. Then I'm going to have a plus 5p because the negative 5p is in essence being added. I'll add that product to both sides. Then I'm going to subtract this product from both sides. And so I would have a negative 4 here, and that is all equal to 0. That I'm not pleased with. Something. Okay, if that were a plus 4, life would be good. Let's look at the problem again. I have a plus 5p and a negative 4. Okay. Let's see what we get here. This is going to be a 2, 3 and a 1, 6. This is a 2, 2. So I better write that as 6, 1 and 3, 2. Those are the pairs I'm looking at. And the key again is what? The negative here, a difference. And as I look at those, wanting a 5 in the middle, as I carry those through in my head, I have a 6 and a 4. I have a 12 and a 2, a 1 and a 12, and a 4 and a 6. What am I leaving out? Ah, I didn't put the 4, 1 there. That will make a difference. Nothing was working. Okay, I missed the obvious, a 4, 1 for the 4. Now let me try that, and I see this last one at an 8 and a 3, which gives me the difference I need. So that tells me that I'm going to have p plus 1. Then I need the binomials written in. So I'm going to have, we said it was this one and this one is what I'm pairing together. So I'm going to have 3 times p, 2 times p. I have a 4 and a 1, and I wanted the 4 multiplied by the 2. So I'd have an 8, and then subtracting off the 3, but I want the 8 to be positive, this as a negative. So now I have a product of 3 factors equal to 0. So I take each factor and set the factor equal to 0. So if I look at the solution now, it is saying that p plus 1 is equal to 0, or 3p plus 4 is equal to 0, or 2p minus 1 is equal to 0. Well, that gives me a solution set that's going to contain 3 different values. P then is equal to -1. So looking now at the solution set will contain a -1. 3p equal to -4 will give me -4/3. And then this one, 2p minus 1 equal to 0, gives me 2p equals 1, therefore 1/2. And I have 3 different values. Hopefully that resolves the question for the person who sent it in. Number 65, if we go back and look at the solution there, it is a difference of 2 squares. Let me write that one on the board, number 65. And I have k plus 3 quantity squared minus 2k minus 1 quantity squared equals 0. The difference of 2 squares, a sum and a difference. So I have k plus 3 plus, I think I'll do this just to make it a little bit easier to see, square brackets, so that is the sum, multiplied by the difference, and that is to equal 0. Then it probably is better to simplify this as 3k plus 2, and here I have minus k plus 4. Then I have 2 simpler looking factors. So I'll set each of these 2 factors equal to 0. And then, going one step further, 3k is equal to -2. K equals -2/3, or minus k equals -4, which we would write as k equals 4. The solution set then is a set containing 2 values at -2/3 and 4. Any question there? Okay, how have I done this differently?
Well, I just multiplied them out and then added everything together and factored them.
That's what I did too.
Okay.
I did too.
Interesting.
It was the first thing I saw.
Okay.
It was easier.
If you look at the original statement up here, obviously you could have expanded both of these, then combine everything and factor. What I was keen on was that this is in the form of something squared minus something squared equals 0. So I had a very straightforward factoring. The other works, obviously, but this is perhaps, if you expand everything, that typically could get you into a pile of trouble. Just from the standpoint, you don't always have the guarantee everything's going to collapse nicely. For example, if I'd had this to the 3rd power in each case, and you had to expand something to the 3rd power rather than seeing it as the difference of 2 cubes, life could indeed be more difficult. So, interesting. Any other comment on this problem? Okay, let's come back to the document chem. And as we look at the 63rd and 65th problem, they are very similar if you see it in the approach we used on the board. If you expand, I hope you didn't expand in 63, because that would have been a real can of worms. Okay. Well, that takes care of one page of requests. Now, the next one, let's see. Okay, that one I think we're okay on. Now the next one's going to require that I go back and look at 317. So before I do that, are there questions for you on the current assignment that you would like to discuss? Those were two that were sent in on email this morning. Do you have a request? Yes. 6-1? Okay, well, I'm fortunate. It's sitting right there on the screen. 6-1. Now, the key in this case is seeing the variable in every term. The variable is sitting there in each of these terms. So let me again write the problem on the board. That is r to the fourth. Then that is equal to 2r to the third plus 15r squared. Is that correct? And I should have said a 3 here, and I wrote, or should have written the 3. Now do I have it written correctly? With the 2r cubed and the 15r squared, is that correct? I guess the first step might be this, just in general get everything equal to 0. That's certainly advised. Then you have to see r squared as a common factor for every term. Then I'm looking for the trinomial with the idea of factoring it. Now the factors for the 15 are the 3, 5, the 1, 15. I want a sum. Is that correct? Yes, it should. Well, what I was noticing, what Debbie was picking up on just about the time I was, there's no way I can get a plus here and get the -2. So my next thought was, okay, did I write the problem correctly, and then did I do all the steps? And I should have brought this across as a -15, and that now will allow me to get a -2 for the center because I need a difference of 2. Now that brings up an interesting point. If you find something not working, the most logical thing to do is go back and ask yourself, did I write it correctly? Then if I wrote it correctly, what would I need to make this work? I would need a difference of 2. Well, I have factors of 3 and 5, so did I miss a sign? And you can sort of go back and debug your process. Now, if this had come out a +15, I could not have factored it. Well, at this point, I now have r squared. I have an r here and an r here. I'm going to go -5 and a +3. That gives me a -2 in the center. Now, I technically have 4 factors here. r times r minus 5 times r plus 3. So this, I'm simply going to do it in this way, rather than repeating the r twice. That gives me the 3 possibilities. Well, r equals 0 is clearly what's going to work here. R equals 5, or r is equal to -3. So my solution set is the set containing a 0, a 5, and a -3. Are we okay there? Does that answer the question? Okay. Anybody else in this one? Any other questions on the homework problem? Okay, if you could pass those on to the side, I'd appreciate that. We'll just leave those up on the table. Now, the question that was still sitting there, as this was after the lecture, I believe. This was on 317, and the question involved a grouping of problems such as 9 and 16, and I'd like to address that again. And this is going to come back and restate something I have talked about earlier. This is on page 317, number 9, and we'll look at that first. Now note This is an expression at this point, so we aren't solving anything. But the question in this problem on number 9 was, as far as the solution is concerned, how do I know that I have to break the middle term into two pieces? Okay. My response was, you don't. You could, but I don't. I use FOIL. This gets back to that question whether you regroup. Perry and I had some discussion about that a few days back, where we said the text provides an alternative to factoring, where you see a middle term and you break it into two pieces, and you do it in such a way that the product of your first and last term is going to involve the product, I'm not saying that well, is part of the decomposition, is the way I guess I'm trying to say that. I'd rather not battle that. The only time I'm going to group 4 terms is when they're given to me as 4 terms, and I can't simplify them in any other way. So let's look at this problem again. Number 9 is a trinomial. I will factor it as a trinomial and use FOIL. Now number 11, I don't have a choice. I have to group terms in number 11. But if I come down to 17, what's my first thing I'm going to do in 17? Combine the like terms and get it back to a trinomial. So my argument, and this was the concern expressed, my argument is avoid 4-termed expressions if you can, simplify them to 3, go FOIL. If you can't, then do grouping. That's a philosophical argument in many ways. Now my defense of that is simply FOIL lends itself to what we will do in later sections, where you have to factor in your head quickly. And decomposition, if you will, breaking it into a 4-termed expression, doesn't lend itself to doing it in your head. But FOIL does. And so we want to do something as a mental process, and that's where I'd like the effort. So the answer to the question, again, if you're given a trinomial, leave it alone, do FOIL. If you're given a 4-termed expression, try to simplify to a trinomial. If that does not work, then group by pairs and see if you're in luck. And there were a host of problems of a similar nature. Number 16 was another one in the same way. But if I look at 16, then in 16 there's no grouping here. This is just taking out the greatest common factor. We did this one yesterday and had 50 times the quantity z squared minus 2. If you'll remember, I talked about taking z minus the square root of 2 times z plus the square root of 2 and looking at that as an extension of the factoring we've talked about earlier on. In something like, and there's several in this list, and it just provides a nice review. Let's go to 44. In 44, the key here is to see what's not there. Namely, 125 is 5 cubed. And you're looking at the 8m cubed, and you're seeing that as the quantity 2m in parentheses to the third. So you have a cubed plus b cubed. Okay, coming off that, if I'm looking through the list again, just seeing if there's anything else I want to comment on. 32. Okay. And 32, just looking at that, the key is the greatest common factor. Now, again, technique. You're looking for, whenever possible, forms. A to the second minus b to the second. A to the third minus b to the third. A to the third plus b to the third. Or a squared minus 2ab plus b squared, trinomial perfect square. A squared plus 2ab plus b squared. If none of those work, and I have a trinomial, FOIL. If I have something that's not a trinomial, then go ahead and try to group and gain some hope. Bottom line, there are expressions that are prime. and nothing works. Now that gets back into that idea you have to know when to stop. There is no nice way of giving you a rule of thumb there. If you've expended all of your resources, everything that you knew to try won't work, then I guess the next thing I would come back and make sure I wrote the problem correctly. Make sure you haven't made some error, as I just did in the board where I lost a sign. Check all those things to make sure that you do have the right problem and you have changed your signs correctly. And if it still can't be factored, let it go. And then, if you have some concerns, ask about it in class. On a test environment, it's hard to let go. But it's better to let go and go on and get all the other problems done and then come back at the end and see if you'll see something that you just, because of the stress at the time of the test, was difficult for you. And if you finish everything else, you sort of let go and say, okay, I'm done. It's like walking out the door. And then suddenly, all the things that you were trying to remember come flooding back, and you hope that happens while you're still at your desk and have an opportunity to change some of the things you've written. Any more discussion on 317? I will get those back to you tomorrow. Okay? Well, moving on. Five, six. We've learned how to solve quadratic equations, and of course the question, where would you get a quadratic equation? Applications of quadratic equations. From a natural point of view, let me give you two examples of where you might see quadratic equations. Thinking of how you would use algebra. There are problems involved with gravity. I'm going to put it that way. Remember I made a comment to you earlier on. Okay, again, I'm trying to be careful because sometimes I reference algebraic content in the stat class. We have talked about a parabola in here because we graph them. And I mentioned to you the parabola occurs naturally when you throw something. Because as gravity works on it and you throw something up in the air, the gravity is working against the force you applied to the object, and so it comes back down. You get a parabolic arc. The equations involved in objects falling are quadratic expressions, second-degree terms. And it has to do with 16 t squared, 1/2 gravity at 32 feet per second, which is 16 then when you take 1/2, and t squared, the square of the variable, which would be time. That gives us a quadratic expression. So they occur very naturally that way in physics classes and in some of the problems that will be given to you in an algebra course. Another place that you're going to see quadratic expressions occur in the Pythagorean theorem, which involves triangles. If I have a right triangle, that means a 90-degree angle, then we have the two legs and what is called the diagonal. The phrase used in geometry is the hypotenuse. But you have two legs and a diagonal. And if we call the parts of the triangle A and B legs and the diagonal C, then there's a statement that says the square of the length of each leg, so A squared plus B squared, must be equal to the square of the diagonal. Well, clearly you're going to have second-degree expressions involved. And if you don't know one of these sides and you do it in terms of a variable, you could quickly get an expression that's going to involve a quadratic expression. The Pythagorean statement is given to you in 327. This is the formal statement, the hypotenuse and the legs, and the C variable. I'm going to be a little bit careful there because language-wise I've said variable. Technically A, B, and C are not variables. We usually think of X and Y and Z as variables. So these are like formulas. A, B, and C representing the legs and the diagonal. C is always going to be your diagonal. Okay, so that's a fairly common notation. And the Pythagorean theorem then simply states that a squared plus b squared equals c squared. So we look at this again. There's your formula. And you, by nature, don't have in that formula anything that would suggest a variable. But what if I tell you information about the triangle? And this is sort of a silly example, but here's figure 3 in page 328. X is one side, the other side is x plus 1, and the next side is x plus 2. We'll come off that for a moment. Examples can be contrived and seem like they are practical. There is in this problem of the Pythagorean theorem, and by the way, Pythagoras lived about 500 BC at a school, and the theorem itself has literally hundreds of proofs that have been given for the theorem. But it was a very important step because of what effect it had on mathematics. Let's come back to the diagram for just a moment. Notice it was x, x plus 1, and x plus 2. And I'm going to have to go over there, so thank you, Debbie, for anticipating that. I'm going to draw a right triangle, and I'm going to talk first about the numbers that work in a right triangle. And this one I have done, have I got this in the same orientation that it is on the book? Let's look. Yes. The right angle is on the left side. That's not an error. We sometimes put a little box down there to indicate this is 90 degrees. We say that the leg is perpendicular to the other leg. Typically, that relationship is given as a Pythagorean triple, 3, 4, 5. So note, 3 squared plus 4 squared equals 5 squared. And indeed, that checks. A 9, a 16, and a 25. 25 is equal to 25. And so if I want to take a problem and rig it, I can argue that I have x, x plus 1, and x plus 2. Can you see that immediately? If this is x, then this leg is x plus 1 and the diagonal is x plus 2. So as I look at that problem, I know that x squared plus x plus 1 squared is going to have to equal x plus 2 squared. Now, this brings up a question. Is this a unique situation? Is there only one such triple, 3, 4, 5, that will work? And the answer to that, by the way, is no. There are other numbers that will work. But let's see what happens here first. And then, as I say, there are a couple other caveats I want to add to this problem. And Pam, this is done more in the spirit of what you were talking about, where you expand everything and then bring it all together. And there is no shortcut in this one. So you expand everything. I have 2x squared plus 2x plus 1, simplifying the left side. Then I'm going to bring the right side over. And when I do that, I'm going to have x squared. I'm going to have minus 2x. And I believe I'm going to have a minus 3. And that's equal to 0. And this one's hopefully very clear. We want a difference. We want a difference of 2. The factors have to be what? 1 and 3. There's no choice there. So as you look at this, you get an x here. Now this is there's so many things in this problem that are important to bring to your attention. It's a little bit hard to sit there and say, okay, take long enough to finish the problem and then discuss it. Having trouble and patient to get to the other interesting things involved here, but let me finish this out. Now, is it clear what I've done in the solutions? Now, I made a comment to you, I think it was yesterday, although there are times when what day I've done this does not relate. I said extra solutions, extraneous solutions, for various reasons. X is to represent what? The length of the short side of the triangle. So I could say up here, let, and you always want to indicate what your variable represents, let x equal the length of the short leg of the triangle. Does it work to say that a leg can be -1 in length? No, length is a positive number associated with a segment, a line segment. So I have a solution that makes absolutely no sense in the problem. Agreed? No sense whatsoever. X equals 3 is the only solution that is relevant. And if x is 3, then if I have to answer the question, what are the lengths involved, then I come back to 3, 4, and 5, and that answers the question. Now, this is a rigged problem. You know what numbers are going to work, and so you write a problem to make it fit. I want to come back to this for a moment. There are several different issues involved here. I want to look at this particular triangle. And let's see if I can get this so it seems reasonable. Okay, so I'm at 30 centimeters there. I'll just put this up here, try to get 30. Well, I did it there, okay. I'm going to create the diagonal. And in creating the diagonal, I have a classic problem out of early mathematics. If this is 1 unit, and this is 1 unit, and I want to know what is x, so that this is a right triangle. The Pythagorean theorem says what? 1 squared plus 1 squared equals
X squared.
x squared. Okay. In the next step, I would have 1 plus 1 is equal to x squared. Now, just out of curiosity, does anybody have a sense of where I'm heading with this? It was yesterday's reference that I already referenced once this morning. Okay, I've got one of you catching.
Well,
Maybe 2.
yeah.
Jennifer, was that? No, that was just notes that you know. Okay. Set everything equal to 0. And what did we say yesterday about that problem? Technically, you can factor the left side. And we get 2 solutions. A positive and negative square root of 2. Okay. Now, the interesting problem was that this would be a fraction, a rational number, because early on in mathematics, and this is following that period after Pythagoras, it was thought that numbers were, at worst, fractions, rational. Now, this had to be a number that was irrational. And the big push then was to argue that the square root of 2 could not be written as a rational number, therefore had to be irrational. And that was upsetting for a society that said number had to be fractional at worst. By the way, just to argue this, so you can see a little bit what's involved here logically. The argument was, assume this could be done, that you could write the square root of 2 as a ratio of p over q, and here's the very necessary observation. P and q are relatively prime, meaning they have no common factor. That has been reduced. So p and q, a fraction, q not equal to 0, and p and q have nothing in common. Now, this is a form of logic that we're going to go through here briefly that is called reductio ad absurdum. Reduce something to an absurdity. You have a choice. Either the square root of 2 can be written as a common fraction or it can't. Let's assume that you can reach a contradiction and you're forced into then the necessary conclusion that it is irrational. Assume you're innocent in a court of law and try to prove that you have to reject that assumption. You are therefore not innocent and therefore guilty. Now, this is a form of proof. It goes all the way back to Euclid's time, 2,000 years ago. Square both sides. Agreed so far? Cross multiply. This would then imply that p squared is what? 2q squared. By cross multiplying. But that says p squared is even. Now the next step needs a little bit more than what I'm going to argue. I'm hoping it seems reasonable to you, and that's the hard part. If p squared is even, the implication is p is even. Therefore, p is even. We can write it as 2 times something then. So I'll say 2k. Just some number. If a number's even, I can write it as 2 times something. Okay, let's substitute. That says then that 2k squared equals 2q squared, if that's the case, because I knew p squared was equal to 2 times q squared. That's 4k squared equals 2q squared. Let's divide both sides by 2. So that says q squared is equal to what? 2k squared. But that says q squared is even. But if q squared is even, what's true? Q is even. Contradiction. Why is it a contradiction? Said they couldn't have anything in common. P is even, Q is even. Here's the key part. P is even, Q is even. But we said the assumption was right at the beginning that P and Q had nothing in common. This is a contradiction. Thus, the square root of 2 cannot be written as a rational number. So we had to do what? Extend our whole concept of numbers, thus the reals. And it all went back to the Pythagorean relationship for the diagonal of a square. Okay? This was extremely upsetting in early mathematics. We had to extend our number system. Now, there's an apocryphal story that's passed down in the history of mathematics that the person who did this unthinkable, suggesting there was a number that wasn't like all the other numbers, the Sesame Street of numbers. Here's one that's not like the others, that they were so upset with this person that they put them on a boat out in the sea with no food, no oars, and sort of let the gods decide what happened to you. the idea was so unsettling that they tried to do away with the person who had the idea. And of course, once the idea was there, that didn't get rid of it. It continued. What about other numbers that work for the Pythagorean theorem? Try this triple. Does it work? Five squared plus 12 squared. Is that equal to 13 squared? I was hoping after our discussion of perfect squares and perfect cubes that this one would be much easier than it appears. What is 5 squared? 25. 12 squared? That's your gross. 12 dozen. And 13 squared?
169.
169. What you can do is 12 plus 1 quantity squared. Okay, but if you didn't, and you knew 12 squared, you could do 12 plus 1 quantity squared, which says you have what? The square of the first, 144, plus the square of the last, and plus twice the product. The product is 12. 2 times that is 24. Add that together in your head, and you get 169. Or, as Barry said, you just know 13 squared is 169. How do you know it ends in a 9? Because 3 times 3 is 9. Well, anyway. 5, 12, and 13 is another Pythagorean triple. Now, how would you write a problem with x as the short side? What would be your triangle this time? X and?
X plus.
Okay, if this is x, what is 12?
X plus 7.
Okay, x plus 7, or 2x plus 2, or 3x minus 3. Okay, x plus 7, and then take the other one maybe as 3x minus 2. So if I could write a problem and write it in a verbal way where I say you have a distance and somebody else goes 7 miles more than that, and the next person goes 2 miles less than 3 times the original distance, and all these distances are on a right triangle, you could then argue that x squared plus x plus 7 squared is equal to 3x minus 2 quantity squared. And now, is it a more difficult problem?
Mm-hmm.
Only to the extent x plus 1 and x plus 2 are nicer than these. Will you quickly go through these? Now, square them. Solve it. Should take you 2 minutes. More or less. On paper, will you complete the solution here? So you have to square some things, put everything on the left side, get a trinomial, factor it, and get the solutions. Let's see if you can do it. And, oh, by the way, you should get a 5 when you're done. Okay, if you don't, we're in trouble. So I'll let you work on that and just leave it up there for a moment. Give you a chance to work on that. I need to get another piece of chalk. Okay, so I'll give you a few moments. You want to zoom in on that, Debbie, a little bit so people at home can get a better view of it? Now the argument is you can whip these squares out, lickety-split. That's a nice non-academic sounding phrase, lickety-split. You should have already had this written down. X plus 7 quantity squared, x squared plus 14x plus 49. Then your 3x squared, 9x to the second, double the product, that's negative 12x plus 4. That should have been possible in your sleep, nearly, at this point. If not, practice, practice, practice. Next step is to do what? Well, you could bring everything to the left side, and then you'd have a negative x squared. So why don't we bring everything to the right side. So 0 is on the left. Then I'm going to have 7x squared on the right. Then what? Minus 26x on the right. And do we agree? Oh, this is a much more interesting problem. What are the factors of 7? Well, that's not interesting. But all 1 and 7 and 7 and 1. But 45 is a lot more interesting because I can have what? 3 and 15, 5 and 9, and clearly the 1 and 45. Does that do it? We got everything? 5 and 9. Well, what I did is reverse here. So if I reverse here, I can just do the 5 and 9 and not have to reverse it. Now, what do I see there that tells me what I want? If I know I need a 5, this better be one of them. Okay, 5, 9, and I want a 26, right? So if I take 7 and 5 and get 35 and subtract 9, I'll have the 26 because I wanted a difference here with FOIL. Okay, let's do that again. I wanted a difference of 40. I'm sorry, I wanted a difference because I had negative 45. I must get the difference at negative 26. My argument is if I use 1, 7, and use the 5, 9, the 35 and the 9 as a difference give me the 26 I need. So if that's the case, and I think what I'm going to do is walk off camera just for a moment, Debbie. I need some room there, and I need to get an eraser to do that. I'm going to go ahead and eliminate this that I did right here so I have room to write the factoring. So 0 is equal to, so we said we'd have a 7x and an x, then what? We said we'd have the 5 and the 9, and I wanted the 5 times the 7 and the 9 in here, and I need a negative 26. So this has to be the negative, this has to be the plus. Set each factor equal to 0. You may see it better on the monitor. So that says 7x plus 9 must equal 0, or x minus 5 equals 0. Thank you. 7x plus 9 equals 0. So x, I'll just put this down as minus 9 over 7. A solution that makes no sense. So I'm not worried about that. Or x equals 5, and indeed, that is the first of the triple I gave you. Two problems involving the same idea. One, pretty easy. The other, not so easy. Pythagorean relationship. I hope what pops into your head, gee, is there anything else besides 3, 4, 5 and 5, 12, 13? The answer, yes. They get worse. We'll leave it at this. I'll leave that on the board. And we have done the kind of problem involved. Here is the way the text, and I don't know if I like this, leg squared plus leg squared equals hypotenuse squared. Okay, yeah, but you don't square legs. You square numbers. Okay, so I'm a little bit bothered by that statement. Legs squared. Next thing we'll do is square heads and square feet. Okay, another one out of geometry. rectangles. This is on page 330. Now, I think you could talk about areas of triangles, areas of rectangles, parallelograms, trapezoids ad nauseum. Page 330, problem number 5. And if you look at the problem, it's somebody fabricated and say, gee, if you had two sides of the rectangle and x has 8 added to one and subtracted from the other, you get a rectangle whose area has to be a certain number or you can't do it. It turns out to be 80. Now, I hope that's sort of obvious that you're going to do what in this problem? X plus 8 times x minus 8 equals 80. Let's look at the problem again. X plus 8 times x minus 8 will equal 80. Then you're solving it. So much for that. Not very exciting. The parallelogram in number 6 is a little bit nicer because the area is 45, and you just have to know how to find the area of a regular parallelogram. And in this case, because if you think of cutting off this triangle and bringing it over here, it would create a rectangle, then you're just going to have 2x plus 1 times x plus 1 again is 45. So not exciting. So thus far, there's not much excitement here. Well, we can get the problems a little more exciting by drawing pictures with cars. Now you have two cars starting from a common point, going one in the x direction, one going in the y direction, and one goes 24 miles. You know x for the other one, and somebody tells you that the distance between them on the diagonal is 4 more than 3 times the distance this bottom car travels. Bottom line, you get what we've been doing. Now, my triple was a 5, 12, 13. You can double each of those numbers, 5, 12, 13, and get a 10, 24, 26. That suggests maybe what's happening here because we have what? So we look at the problem, a 24. Maybe. Okay, now the question. Where does the problem talk about? We'll see how they've written this to make it exciting. Two cars leave an intersection. One goes north. The other goes east. You better have a sense of direction or you're going to be in trouble in this problem. The car traveling north goes 24 miles. The distance between the cars is what? 4 miles more than 3 times the distance traveled by the car heading to the east. Now that's taking information that you then should translate into this diagram. Now I'm hoping that that seems reasonable in a translation. We're hoping. Okay. I mentioned to you throwing things into the air. Let's just go to here. Okay. An object is propelled upwards from a height of x feet at an initial velocity of v feet per second. I mentioned to you classic physics. Well, here's the equation. H equals minus 16t squared plus vt plus s, where h is how far you're in the air at the beginning, v is the velocity, and the value of s has come off there for a moment. Let's see if I can give it to you in terms of, let's see, I'm looking for where they give you the explanation of the various letters. And I guess they're taking s as the distance originally, which was, as we come back to the diagram, 48 feet. The point here, they don't expect you to translate this particularly. They give you the resulting equation. Now, what you want to know is when is the height 0. So you put h 0 and you solve. Not a particularly difficult problem. Well, what we're going to do is take an assignment of some of these and have modest amount of fun. Okay? There is nothing particularly relevant in the problems I'm going to select, and I have to do this in about 30 seconds. But number 5, we talked about that. Then number 7, just because it's another one done in much the same way. Number 17 and number 20 and number 22 and number 25 and in number 27 and then in number 32, well, let's make it 33. Number 33, I have 1, 2, 3, 4, 5, 6, 7, 8 problems, 8 word problems. I don't know if that's quite accurate. Number 5, 7, 17, 20, 22, 25, 27, 33. And I'm seeing if there's anything else on the next page. Yes, let's do number 39. We'll do 2 more. Number 39 and number 41. With that, what are we going to finish out here, Debbie?
Bridge over troubled water.
Bridge over troubled water with Simon and Garfunkel. Have a great morning.